please take a closer look at the electromagnetic emission. Because this is a typical electromagnetic emission plot of an IC. The y-axis defines the amplitude of our noise signal. As I mentioned, very often given in dB microvolt. The x-axis is clear as the frequency. And now look a little bit on the waveform and how this electromagnetic emission looks like. Do you see something which is strange or interesting or? The electromagnetic emission falls down, so it not stays at a very high level. So we can ask ourselves why the electromagnetic emission is decreasing here at a certain rate. This is something we can discuss then. It would also be interesting, why is the electromagnetic emission here in this frequency range looking like this? So it just goes down, 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 very smoothly. But here we have some spikes that are coming out of this electromagnetic emission.
So the measurement range stays the same, or the field, the frequency span I inspect stays the same for now. And that's the reason why I have like the volume at the beginning.
Okay. Yeah, let's discuss this a little bit. That's good. Then also look at this thing here. So we are coming down with the electromagnetic emission. Okay, there are some spikes coming out. This is not the noise floor. The noise floor is somewhere here at about roughly whatever 0 dB microvolt or minus 10 dB microvolt. So this is still electromagnetic emission that is generated by this IC. So we have some spikes coming out of here. Take a closer look here at this frequency, 30 megahertz. So suddenly the electromagnetic emission jumps up here and then falls down. And okay, here, this last peak here, it might be not related to the IC. What's the frequency range of this last peak here? 900 something megahertz. It might most probably be a GSM signal that we were capturing, because we were not using an anechoic or the shielded room to make the measurement. We just placed the printed circuit board with the device on the desktop, made the measurement. Okay, but I'm pretty sure that all this electromagnetic emission that you can see here is related to the switching activity of the IC. Okay, then step by step, let's go to the most important things that we can extract out of this plot. So first, let's focus why we have this rise in the electromagnetic emission, which is very sharp. So can the electromagnetic emission of an IC just jump over whatever it is, 10, 15 dB microvolt? Not if you're measuring in the right way. As I said, we have to measure at each frequency position at least 3 times the operation cycle of the IC. If you're violating this rule, then it can happen that we are at a certain frequency position and suddenly the microcontroller wakes up and produces more electromagnetic emission. So this can happen then that there are certain frequency ranges where we have increased electromagnetic emission. But let's suppose we are measuring in a correct way. We are waiting at each frequency position as long as needed. So any idea what happens here? Because this is usually what the customer is asking. Hey, why is the electromagnetic emission here higher and why is it jumping up?
Does it something have to do with the resonance frequency of the capacitor? Since it changes phase from the capacitor side to the...
Okay. No. Simple answer, no. Why not? As I said, we are waiting at each frequency position for a long, long time. So usually all the electromagnetic emissions that are generated by the switching activities of the ICs, not just one switching activity, there can be many, many different switching activities. They are during this time frame sometimes always in phase. So for example, I have 5 different sources of the electromagnetic emission, and a certain resonant that is built by a capacitor in combination with a parasitic inductance in the package can cause a certain resonance effect where I have increased electromagnetic emission in a certain range. This is possible. But let's suppose this is also the case, then all the electromagnetic emission that I'm measuring is at least sometimes in one phase, and I'm measuring the maximum electromagnetic emission of all these noise sources. Especially when I'm using the peak detector. I have not mentioned the detectors yet, but let's suppose that it's with the peak detector. Okay, I don't know. Okay?
I think the reason is that I switched the frequency span of measurement. These frequencies, so I have two parts I measure.
Yeah. Yeah. Okay, yeah, it comes very close, but it's not really the frequency span. Frequency span is usually, yeah, I have to explain a little bit more what's the difference between an EMI receiver and a spectrum analyzer. Basically, they are the same. The frequency span is usually the frequency range between the starting frequency and the stop frequency. So I can define in which frequency range this thing. But it has to do something with that because I'm changing something. I'm really changing some settings at the EMI receiver at this frequency range or at this frequency position. But actually what I'm changing is
that's the input bandwidth.
Exactly the resolution bandwidth of the input filter. And this is the reason why we have a jump here. So let's focus on that. Why do we have to change the resolution bandwidth of our input filter? So each spectrum analyzer or EMI receiver has different input filters. The spectrum analyzers usually have 10 kilohertz, 100 kilohertz, 1 megahertz or something, or 100 hertz. The EMI receivers have different values. They have 9 kilohertz, 120 kilohertz, I think also 1 megahertz. Okay, just okay. But any idea why we have to use certain resolution bandwidths within the whole frequency range? And why we have to use different resolution bandwidths? Because it seems that over this frequency range we have one resolution bandwidth, and over this frequency range we have changed it to another resolution bandwidth. So let's first focus on why, and then let's talk about what have changed, how we have changed it. So what's the main purpose of doing all these electromagnetic emission tests? Why are we doing this?
Yeah, to see in which frequency range we have the most emissions, and maybe to track down then the source of this emissions.
Yes, very good. The original idea in the 1960s, when they started doing these first measurements, or when the first regulations came out, was really electromagnetic interference of the radio reception. During these days, this was the most important thing, that we have electronic systems which are not producing too much electromagnetic emission, that the radio reception is very clear and we have no interference with the radio and radio communication. If you think of your radio that you have at home, not the digital radio, the old-fashioned analog radio, so you can tune also different frequency ranges, especially in the FM range from 88 to 108 megahertz. And what's the frequency separation of all the, or what's the slowest frequency separation when we have quite a lot of FM radio stations? So how far are they away from the frequency range? Yeah. I'm not 100% sure if I can give you the right answer, but I think it was defined 120 kilohertz. I think this is then also the reason why we have a resolution bandwidth of 120 kilohertz, because we are interested in what is the total noise that is present at one frequency, at a certain frequency position, with a 120 kilohertz Gaussian filter. So every noise that is present within this 120 kilohertz range is measured and displayed then on the EMI receiver. Okay, this is for the FM range. FM range is then somewhere here around 100 megahertz. But actually, the whole definition of the frequency range starts at here, 30 megahertz, and goes up to 1 gigahertz. So in the whole this frequency range, 30 megahertz to 1 gigahertz, we are using 120 kilohertz resolution bandwidth. Or 100 kilohertz if you are using a spectrum analyzer. And then here in this frequency range, so slightly you can see some limits here, and also here. These are the frequency ranges for the long wave, middle wave, short wave radio reception. And there, the resolution bandwidth is 9 kilohertz, or the separation of the channels had to be at least 9 kilohertz. So all this stuff comes from the radio reception, and now we can ask ourselves the question if it's still that important, because who is listening to AM or long wave or middle wave radio anymore? But still we have the regulations and also the limits here, so we have to fulfill these requirements to be below the limits. And nowadays, as we have more and more digital radio, maybe also a 120 kilohertz bandwidth doesn't make that much sense anymore, because the bandwidths of all the communication systems today are completely different from 120 kilohertz. But currently the standard says measure in different frequency ranges and use from 150 kilohertz to 30 megahertz 9 kilohertz, and from 30 megahertz to 1 gigahertz 120 kilohertz. Okay, so now we have defined the resolution bandwidths. And the next thing is, why is the frequency or the noise signal or our electromagnetic emission increased here?
Because the bandwidth now is wider and with more frequency components.
Exactly. We have a wider bandwidth because over this frequency range we are using now 120 kilohertz, not 9 kilohertz. So more noise and more electromagnetic emission is within the bandwidth. And this is the reason why we have this jump over there. So if you're asked by a customer, oh, why is the emission increasing? This is a weak IC because the emission is jumping. Then you can calm the customer down and say, no, it's not the IC is not responsible. It's just the standard which defines to use different resolution bandwidths over different frequency ranges. And if I'm changing the bandwidth from 9 kilohertz to 120 kilohertz, more noise and more emission is within the bandwidth, so therefore also our emission level is increasing. You can directly calculate how much is it increasing. 9 kilohertz divided by 120 kilohertz, logarithmic times 20 should give you a value of, I don't know, so much. Roughly so much. Okay, so yeah, what else is interesting? Any idea why we have an electromagnetic emission that looks like this over here, and then we have some spikes coming out of the electromagnetic emission? As I told you, inside of the IC, there are many different sources of the electromagnetic emission. It's not just one source. And in this IC, we have at least two dominating sources of the electromagnetic emission. I'm step by step guiding you in the right direction. The IC is a smart power automotive high-side switch. Just a switch which can be turned on and can be turned off. For example, to control whatever, the front light, to turn the front light on of a car or turn it off. And the front light is very often operated at 100 hertz, 50% duty cycle. So the switch is opened and closed at 100 hertz. And inside of the chip, there is a power switch. The power switch is a transistor. In this case, it's a DMOS transistor. And it's an N-channel transistor. So there are P-channel and N-channel transistors, and very, very often we are using an N-channel transistor. Now I can ask the question, why are we using an N-channel transistor rather than a P-channel transistor? Why are we more often using an N-channel transistor than a P-channel transistor?
I think it's better to produce than a P-channel, so it's a smaller die size for the same ISO.
Mm-hmm. Yeah. Faster, smaller, better. It has something to do with the mobility of the charges. So in the N-channel transistor, it's the mobility of the electrons, and the P-channel transistor is mainly the mobility of the holes, or the defect electrons. And the mobility of the electrons is, yeah, at least factor 2 to 3 higher. So therefore, we have, for example, smaller feature sizes, smaller R-on resistances. And the R-on is very important because we are dissipating heat on the internal resistance of the switch, and especially when we are changing the switch from high to low and low to high. Okay, so I also mentioned high side switch. So what is a high side switch? So I have 4 minutes left. This is good. High defines the height of the potential. High side means it's on the high potential. So I have a 12-volt power supply in my car. This is my battery. Then I have a cable harness connecting the battery to my control module. And then in my control module, I have my switch. And the switch is in this case a power switch. Let's make it this way. So an N-channel power transistor, and well, here I have my load. In this case, it's the front light. Okay, so this is the configuration of a high side switch. So the switch is on the high potential side. The other thing is the low side switch, which is then exactly looking like this. So the switch is on the low potential. Okay. There is a special reason why we are mainly using high side switches and not low side switches. Any idea why we are using automotive high side switches and not low side switches? This comes with a benefit, but also with a big drawback.
You probably give a disturbance. Let's say if you have a short somewhere from the low side switch, then you still have the current box exposed.
Okay, so if the cable breaks and shorts to the chassis, then it doesn't matter if the switch is open or closed, the load is always driven. Okay, so it's a safety feature. What happens if I have a short here? I'm just shorting the load, so okay, load is not active anymore. But as it's a smart high side switch, it will recognize, hey, there is a short, and will turn off and protect itself. This is a big advantage, so functional safety. But also cable harness is an important point, because I just need this cable here. Oh, okay, I need a power supply cable to my control module, and I just need this cable here to my load, and the load can be then directly connected to the chassis, which is usually the metal frame, the metal housing. So I do not need an additional cable here. Here I need a cable to connect the load, and then from the load I need a cable to the control module, and the control module is then grounded. And cable is weight. So nobody wants to have additional weight in a car. So these are the advantages and drawbacks. And now let's come to the solution why we have these spikes coming out of the electromagnetic emission. As I said, this is an N-channel transistor. So I need a high signal on the gate to turn the transistor on. Okay, what is the typical gate driving signal that I need to turn a DMOS on? 2 volt, 3 volt, something in this range. So actually, I need a voltage difference between the gate and the source. So a VGS. which is bigger than the VTH, the threshold voltage. And the threshold voltage depends on whatever the transistor is, a couple of volts. Okay, so now comes the problem. If I have my 12-volt power supply here, which is there in my car, here is my control module, and I'm just generating a 5-volt gate signal. And I'm applying 5 volt here. The transistor is at the beginning not turned on, so I have ground potential here, which means that also the source potential is ground. So my VGS is 5 volt. I think it's clear. So VGS is bigger than the threshold voltage. What will happen? Transistor will turn on. Okay? Yeah, but now something strange happens. Here I have the 12 volt. Then there is current flowing. There is a voltage drop across my load. The on resistance of the transistor is usually very small, so I need a very small on resistance, 30 milliohms, for example. So what will happen to my source potential? Will it be 0 ohm as before? 0 ohm, 0 volt as before? No, definitely not. It will raise up to roughly, whatever, 12 volt, also depending on how big is the on resistance here. So a little bit lower than 12 volt. Okay, gate signal is 5 volt, source potential 12 volt. How big is VGS? -7. Is it bigger than the threshold? No. What will happen? It will turn off. So what is needed to keep it turned on? Exactly. I need some black magic. I need something which is bumping up my voltage here to 12 volt plus whatever the threshold voltage. So whatever, 14 volt or whatever is needed. Okay. And now let's come to the reason why we have some spikes coming out of my electromagnetic emission, and we will come to the generation of the electromagnetic emission then on the next presentation, the next thing. But these spikes here that are coming out of my emission that is caused by the 100 Hertz switching activity is mainly related to the electromagnetic emission that is generated by the charge pump. Because the charge pump in this case is operated at 2 point something megahertz, and here we can see all the harmonics of this charge pump switching frequency. And next time we are talking about small band. Too late. Breitband und Schmalbandstörung. Is it broadband and narrowband? This was the thing. Next time we're talking about narrowband and broadband emissions, because what you can see here is a mixture of this broadband and narrowband emission. So maybe as a homework for next time, think about what is broadband and narrowband emission. And as I said, there are two sources of the generation of the electromagnetic emission. One is the 100 Hertz switching activity, and the other is the high frequency activity of the charge pump with 2 point something megahertz. And then you will most probably get an idea why this electromagnetic emission plot exactly looks like this.